Hello and welcome to our session number 41. In today's session, we'll be covering some of the material in chapter 22. Specifically, we'll be looking at channel length modulation, which shouldn't take too long. We introduced it last time. We'll be looking at it a little bit more quantitatively this time. And then we'll go on to the big topic for the day, which is velocity saturation. We'll be doing it both qualitatively and quantitatively. And to get started, we have a kind of an interesting, and I hope you'll find enjoyable, performance of Beethoven's Ode to Joy. And we'll see you in about 3.5 minutes. Here's a list of topics we'll be covering in today's session. The first two deal with channel length modulation, almost entirely a review and fortunately very little mathematics. So that's a good thing. And then we'll be going on to velocity saturation qualitatively, also a review, because we've looked at velocity saturation in previous sessions. And then we'll be going on to the bulk of our discussions, which is velocity saturation quantitatively. Here there'll be a bit more mathematics, but I think some of the expressions that we'll be deriving will be not only interesting, but they have some important ramifications for modern devices, and we'll be ending with a finale to the Beethoven Violin Concerto, a wonderful performance by one of the most important and talented violinists in the modern era, Hilary Hahn. So let's get started. We'll be looking at channel length modulation, and to motivate us, we're going to go all the way back to the BJT. The BJT, it's called neutral bass modulation. And you remember what happens. This is a PNP device. In a PNP device, we have a forward bias on the emitter base junction. The emitter is biased positively, so we push holes into the base, and then those holes are pulled at the base collector junction by the high reverse bias at the base collector junction. So we push them here and we pull them out here, and as we increase the reverse bias, which is to say, as we increase the output voltage, the depletion region increases both on the base and the collector side, more on the collector side, but some on the base side, and the neutral base shrinks. As the neutral base shrinks, the current increases, and therefore we have a slope, and that slope in the output current is due to the shrinkage of the neutral base region. High excess minority carrier concentration. Here, low excess minority carrier concentration. Here, the current is due to the gradient of excess minority carrier concentration, which is to say the absolute values divided by this distance. The distance decreases, the current increases. And I guess one final note, we could draw more of these curves. Each of these curves, if we drew more of them, would be for a different base current, and they all end up somewhere way on the left side in the early voltage, and the early voltage does not depend on the base current, which is kind of interesting. Good early voltages would be somewhere in the 70 to 80 volt region. If the slope was 0, which is unfortunately impossible, the early voltage would be infinite. So we have exactly the same issue with MOSFETs. In MOSFETs, if we have VDS, which is the output voltage, if we have VDS at VD sat at the drain, then the pinch-off point, the point where the inversion charge goes to 0, would be at the drain. But as VDS increases above that pinch-off point, then the point L prime, which was over here, moves to the left, and we get a delta L. So as VDS increases above saturation, delta L increases, the channel decreases, the current increases. And that's exactly what is shown in these two drawings. Here we have pinch-off at the drain. Here we have pinch-off to the left of the drain. The channel in this picture here is less than the channel in the top picture, and therefore the current increases. So we have a slope to the current as a function of the output voltage. And that is manifested in equation 22.1, where this particular equation is written for pinch off right at this point. Pinch off point is right at the drain, so we have the full channel, but as VDS increases, L now becomes a variable. L decreases and ID sat increases. And that is what is shown in figure 22.4. As VDS increases above saturation, then we have a slope to the IDS curve, and the IDS increases as a function of VDS. This is not good. We want the output current to be only a function of the input voltage, VG, not a function of the output voltage. So we have, again, two currents here, just as we had for the BJT. And the question, I won't answer this question. I'll leave it as an open question right now. It's an interesting question. In the BJT, these two curves wound up, if we extended them down, they wounded up at the early voltage, which is a voltage which is defined not by the curves itself, it's a function of the structure. Does that happen here? In other words, if we extend this guy and we extend this guy, do they wind up at the same point? Well, there is no early voltage for channel length modulation, so you can probably surmise that they do not. It's certainly a bit more complicated than the BJT. And in section 22.3, we take these same results we've been looking at for a number of sessions, and we just give them a little bit of a different twist. So this, again, is almost entirely a review. The inversion charge is equal to, of course, VG minus V threshold. We've seen that many, many times. And if we just put that into our basic equation, we have an equation for V threshold. Generally, we do not put the V flat band voltage. I put it in here anyway, so it's not a big deal. This involves the Q depth, which is extracted from V threshold. We've done this a number of times, so I'm not going to go back and review it. The depletion charge is given by equation 22.3. Again, we've seen it a number of times. Does not vary with Y. However, if we put in the requirement for charge balance, then we have a situation where the Q depletion is a function of Y. It increases as Y increases. And again, we've seen that a number of times. So if you write an expression for the output current using 22.4, not 22.2, we get the famous or infamous parameter M. And that is due to the fact that we have the depletion charge, which increases along the channel. So now the VD sat goes down by the function of M, and the IDS, which is equal to ID sat in the saturation region, involves the new VD sat, which has the M, and now we want to take a look at this parameter L, because L is no longer a constant. So we just write equation 22.6 as equation 22.7, taking out the VG minus V threshold divided by L explicitly. And now we want to take a look at L. So if we have VDS above VD sat, then we can rewrite this as the same equation except now instead of using L, we have to put in L prime, and L prime is less than L, and specifically L prime, let's just go back, way back, oh my goodness, way back here, L prime is equal to L minus delta L, and that's all we're saying here. Where is it? It's got to be someplace. Okay, here it is. So L prime is L minus delta L, and we can pull out an L out of the parentheses, and we get 1 minus delta L over L. And if delta L is less than L, which we certainly hope it is, we can expand this as a power series. 1 minus x, where x is delta L over L, to the minus 1 power is approximately equal to 1 plus x. And that's all we're saying here. And as delta L grows, what happens IDS? It grows. And that is exactly why we have the slope. And that's seen right here in the equation 22.9. Okay, so we have the new ID sat, which is equal to the first part of this expression. The difference in the IDS, ID sat, which gives the slope, is given by delta L divided by L squared. So this delta ID sat, we just multiply through by the delta L and take away the original, which is the 1. So let's now move on to velocity saturation, which is our next topic. It's divided into two pieces. One is a qualitative with very little new material and new mathematics, and then the quantitative, which is a bit more challenging, but I think, well, it's a lot more interesting. So remember that velocity saturation refers to a situation where the linear relationship between velocity and electric field no longer holds. This is the classic ohmic relationship, where force is related not to acceleration, but force is related to velocity. This is the situation where one's driving along at about 60 or 70 miles per hour. Just as a personal note, I don't go over 55, but that's just me. So if someone is driving along at 60 or 70 miles an hour, in order to increase the velocity, one must increase the force. The tachometer must rise. Got to push the engine a little bit harder. But there comes a point somewhere in the, 130, 140 miles per hour range, where even if you increase the force on the engine, the tachometer goes to 10 or 12,000 RPM, the velocity doesn't change. There is just so much back pressure. And that's exactly what happens in a semiconductor. The electric field becomes so high, the velocity becomes so large that an increase in the electric field does not produce an increase in velocity. The velocity has saturated. And as we mentioned previously a number of times, that this particular equation has very important ramifications for the current density. This is the current density in amps per square centimeter. And if we have a velocity which is proportional to electric field, which is to say is proportional to voltage, and VDS is proportional to gate voltage, then we have a situation where the current density is proportional to the gate voltage squared, because N is always proportional to the gate voltage. The higher the gate voltage, the higher the charge density in the channel. It is this guy which saturates, and this is no longer VDS over L in the equation for current density. And this paragraph basically just sums that up. This term here is the critical term, and when this term basically flattens out, no longer it depends on voltage, we get not a square law, but a first power law for current density with respect to Vg. And basically that's what this paragraph sums up. This is generally considered a short channel effect, SCE, short channel effect. But it really is a bit broader than that. Short channel effect generally refers to the fact that when the channel is so short, this distance here is so tiny that the pinch off occurs very close to the source region. But it really occurs to a certain extent, even in longer channels. And in fact, I believe that square law has never been observed practically because you're always operating in saturation. So some part of the channel is always pinched off. This equation, this figure, I should say, 22.5, kind of sums up the different regions. Very close. This probably should be pushed over a little bit. This point here really should be at the source. So very, very close to the source, when the charges are just being pulled out off the source into the channel region, then it's possible, at least for a couple of monolayers, maybe 10, 20, 30 angstroms, where we have electric field is proportional to acceleration, not velocity, but that's, I should put a question mark here. Much of the channel is ohmic, where the velocity is proportional to electric field. And then we have a region where the electric field is so high, the Q inversion is so small that we have velocity saturation. So that's kind of summed up in this picture here. And it is the constant velocity, the velocity saturation part, which is going to be concerning us in this section and in the next section. And this kind of long-winded paragraph here basically sums up everything that we've been discussing. So you can read through it. It's not, hopefully it'll be not completely idiotic. Okay, so the bottom line is that ID sat is proportional not to VD sat to the 2 power, but to VD sat to the n power, where n is always greater than 1. There's no equal signs here, and n is always less than 2. It is close to 1 for short channels, very short channels, and it is close to 2 for long channels, but it never gets to either one of those. So these two effects are summed up in the next two figures. This figure, I don't think is terribly clear. What I wanted to say was, first, we have the saturation region, and we never get, if we have a gate voltage is VG1, we never get a curve which is 2 times. So I really should make this higher. This 2 times VG1 is really up here, and the 4 times VG1 is really up here. But the curve, this curve here is less than 4 times VG1, and this is less than 2 times VG1. So we double VG1, we get less than the square law. And if we combine that with channel length modulation, we have a situation where we don't get square law and we do have the slope. So this is a modern day device which has both channel length modulation, which is to say it has slope, and it has velocity saturation because we do not have a square law. So now let's get started on the quantitative, and this is going to be a hopefully a rather interesting journey that we'll take together. Trying to motivate it by, again, a long-winded paragraph which essentially states everything that we've been talking about before. Velocity saturation is like a parachutist who reaches a terminal velocity when his parachute's open. So we have at the large electric fields, large electron velocities, large scattering, and a situation where the velocity does not increase if we increase the electric field. And so look at some numbers. We have a critical value of electric field. We think of this as being a critical value of the tachometer. The tachometer, depending on the air condition, the atmospheric conditions, if it's a blizzard or if it's got a nice back wind, somewheres there is a critical electric field in the range of, this is a range, not a sacred number, about 10 to the 4th volts per centimeter, at which we reach a velocity saturation of about 10 to the 7th centimeters per second. So if we divide the velocity by the critical field, we get a situation where 10 to the 7th divided by 10 to the 4th, we get a mu. Now, we can't really do this because velocity is not equal to mu e, but if we could, we would get a mu of about 1,000, and that's a fairly good number. Mu's range anywhere from mobilities, that is to say, about 100 to about close to 1,000. And of course, the units are volts per centimeter squared per second, which we can see immediately here. So, what do we do with it? Well, how do we put this in a quantitative form? Well, we try, and here's the first two attempts. We'll see one more a little bit later on. Equation 2213a and 2213b, and I'll ask the question, which one is a little bit easier to use? And I think the answer is relatively clear. It's this guy. This is the guy that we're going to be pursuing. So for electric fields much less than the critical value, this term goes away, and we have a very simple relationship. Velocity is equal to mu e. That's our starting point. So that's fine. For electric fields much greater than the critical value, the 1 goes away, and then we divide through, and we get the velocity is equal to, or proportional to, mu times E critical, which is to say it's constant, because E critical is constant, and therefore we get a constant value of velocity, and mu is simply a parameter. So for low electric fields, we get back our original proportionality. For high electric fields, we get a constant value of velocity. Well, let's see what implications that has. Okay, so we rewrite equation 2213b, and since mu is basically something that we're not going to be terribly considered important, but we'll just label it as mu 0 here, just to kind of get it out of the way. And now we're going to put this expression into our current density, and more importantly, into our output expression. So instead of V, now we write, of course, the definition of V is just the first derivative of channel voltage with respect to Y. The channel voltage, of course, is a function of Y. And now we substitute for E, and we get equation 2215. So our goal now in life is to take this equation and its partner up here and get an expression for IDS. Now that is the big deal. So we have IDS over here, and divide by mu 0 and multiply by this guy on the denominator, and we have a new term. Here's our new term, and of course it's just equal to the width multiplied by Q inversion multiplied by E, which is the first derivative of channel voltage. So far so good, no big deal, except we have a new term, and that new term is going to make our life a little bit more interesting. So it's good and bad. Bad because there's some mathematics, good because we get some new results. Okay, so this is the guy now that we have to integrate. If we didn't have this term, everything would be exactly as it was before. We integrate from 0 to L, and we integrate along the channel from the source to the drain. At the source, the channel voltage is 0. At the drain, the channel voltage is VDS. So everything on the right side is exactly as it was before. Now we're going to include the increase in depletion charge. So we have the factor M. This is the new term right here. So this is the part which is going to make things a little bit more interesting. So let's continue. Let's trudge on and see if we can figure out how to deal with this new term. And here it is. We just repeat the equation. The right side, we just go right down, and it's pretty straightforward. This is a very relatively easy equation to integrate. So this is basically exactly what we had previously. Here, let's see what goes on over here. Over here, we first we multiply through by dy, which cancels the dy in the denominator. We have VDC, the channel voltage, which is a function of y. We can integrate on this from 0 to L. It might seem kind of funny to integrate a voltage over a distance, but we just ask the question. It just comes out to be a constant. What's the voltage at the source? Well, it's 0. What the voltage at the top? L, it's VDS. So this part, the dy comes in here. This is just 0 to L, so this is just L plus the integral of this term, which is 0 for the lower limit, and VDS, now not L, but rather VDS at the upper limit. So now we have IDS is equal to the same exact expression here, but a new term right here. Okay, so that looks not too bad, but now we want to find VD sat. So first, let's take a look. We rewrite the equation. This is the velocity saturation term. This is the conventional term. We can just basically call this anything we want. I just call it A. So IDS is proportional to, if we just take out these terms, they don't really add anything. That's why the proportionality constant here multiplied by this term, which is 1 plus VDS over L, equal to the minus 1, because it's in the denominator. So now I want to take the derivative of IDS. That's why I don't have to worry about these terms here, because they're constants. I'm taking the derivative, they all go away. But A is not a constant. A has VDS. So if I'm taking the derivative of IDS with respect to VDS, why am I doing that? I want to find out when the curve flattens out. When it flattens out, that's ID sat, or VD, I should say VD sat, which will give us ID sat. So we just take the derivative, and that is all we're doing here. First we substitute for A, and we still have some constant. This is the constant here, and this is not a constant, but if we actually VDS, it would not be a constant. Because we're looking for VD sat, we can call this a constant. We define that as our constant C. So we have an expression. The first derivative is 0, defined as 0, because that's exactly our criteria for VD sat. So everything comes, VDS becomes VD sat. And the equation, or the issue right now is we can define some constants, and we have to solve this equation for VD sat. And that is exactly what we do. Given the constants B and C, we multiply through and we get this expression here. When I say multiplying through, I bring the LECR to the left because of the denominator. This thing becomes B. This is the definition of B minus VD sat. I also have a term of, let's see, this term here becomes, or B times VD sat. This is just VD sat divided by 2. And this term here is C to the minus 1. So that's reasonably straightforward. Let's see. Because this is C in the denominator, so I just bring this guy, I bring him over to the left side. This is our C, and that is equal to this. VD sat minus VD sat squared over 2. So this is what remains on the right side after I bring this guy to the left and I bring the C to the left. So continuing now, well, the little bit of algebra, what I'm doing here is I'm just opening up the parentheses. So I get the first term is just this guy multiplied by 1, and then I get a VD sat squared with some constants which cancel out. That's this term here. Then I get a B with a VD sat. That's this times this times this. That's over here, and the numerator cancels with the denominator. So these terms are pretty straightforward. And let's see. There must be something else here. There is one more term, which is, here it is. It's the 1 times VD sat times LECR. That's this guy times this guy times that guy, and that is that guy. Of course, there's 4 terms here. There's 2 here and 2 here, and all 4 terms are shown here explicitly, and that's, of course, just equal to the right side. And then I put everything together. The VD sats combine, and there's a 2 here when I bring this over onto the left side and multiply through by minus 1. That's why we get some sign changes here. And let's see, well, I get a nice cancellation here. This cancels with this, and that's pretty much it. And there's the 2 comes from the 2 when I bring this over on the left side. So this is it. This is the equation with B, a constant value up here. That's a quadratic equation. So the solution is given by the, what else? The quadratic formula. And here it sits, where I make another definition of L. It's E critical, I define as D. This is just the quadratic formula. And basically, we are just about done. We're getting very, very close. So we massage this a little bit more. Oh boy, I'm defining constants out the kazoo here. We define another constant here just to get rid of this guy and make it a little bit more palatable. So I get, finally, VD sat is equal to this, where I define this new constant, C. Now, this doesn't look all that great. So how do I make this look a little bit cosmetically more pleasing? I multiply and divide by C plus 1. And if I do that, this is C. This is C. I'm multiplying and dividing by the same thing. So this is just, all this is just 1. But here I have C plus 1. And here, of course, I'm dividing by C plus 1. And if I do that, I get a form where I multiply this guy by this guy right here, and I get C plus 1 multiplied by C minus 1. And that, of course, is just equal by elementary algebra to c squared minus 1. And that is the goal of the exercise. This is c plus 1. This is c minus 1. And that is exactly what I want. I just want to make one comment here. Why did we kind of pull this thing out of the hat? Well, you're looking at something minus 1. Whenever you have some gunky thing here, complicated thing, minus 1, always think about multiplying and dividing by something that will give this same thing plus 1, because then you can have the possibility of getting a square minus 1. So that is a good thing. So this actually came out in a relatively natural way of thinking about things. The idea is to make this simplified. One way to make this simplified is to multiply by the plus 1 because we have a minus 1. So that's what we do here. Again, the d is this other constant, and we multiply the entire numerator out, and we find that everything collapses very nicely. This is just, let's see, we go what, d plus 2b minus d, so the d's cancel out, 1 minus 1, and we get 2b. So all of the numerator collapses to 2b. Again, b is a constant. We're going to substitute in just a minute. And then we have the denominator, which unfortunately does not collapse. Where did this denominator come from? It came from here. Now, we were just working on the numerator, but the denominator, unfortunately, is still with us. It's going to give us a lot of interesting physics, so we need it. So that's a good thing. And now we substitute for b, which is just Vg minus V threshold divided by m. And we substitute for d, which is L times E critical. And that's it. Equation 2223 is an expression for VD sat. So that's a pretty big deal. So we've accomplished quite a bit with a little bit of algebra. So let's examine this a little bit more detail. If we have this term eliminated, this goes away completely, isn't there, then we get the conventional term. This guy would go to 1 plus 1 would be 2, cancel out this 2, Vd sat is Vg minus V threshold divided by m. So in the case where we have a linear relationship between velocity and electric field, we get back the original relationship. Now let's take a look at this term. This is the critical term right here. So if we have a length, for example, of 10 microns, that's really, really long. In fact, that's actually ridiculously long. Then E critical, which is 10 to the 4th volts per centimeter, multiplied by L, which 10 microns, 10 to the minus 3 centimeters, would give approximately 10. Actually, this is volts. Everything here is in volts. This is in volts. This is unit. This is in. Yeah, this is unitless. It's not K. It's unitless. So this must be in volts. So everything is in volts. So if you multiply volts per centimeter times centimeters, of course, we get volts. So this would be 10 volts. So if we have it 10 here, and this term here is generally going to be much, much smaller than that, on the range of 0.1, maybe 1 at the most. So this term will be quite small, and our VD sat will be the conventional VD sat. However, if we have 100 angstrom or 10 nanometers, this guy comes out to be 10 to the minus 2 volts. So I'm putting 10 to the minus 2 volts for this term here. This term dominates very dramatically, and we can no longer assume that VD sat is equal to the conventional term. In fact, it's going to be much different than the conventional term. So when we have E critical times L much less than 1, which is this case here, we can go through the mathematics relatively easily. The 1 goes away. This term dominates. So that's why we have 2 divided by 2 multiplied by this term here. Relatively easy. We just flip it on its end here, and so 2 comes up here. It comes square root of 2. This becomes square root of Vg minus V threshold, and we have another square root of L E critical. So the VD sat now becomes this term. Well, that really doesn't look like a conventional term, because now the VD sat, not only is it not proportional to Vg minus V threshold, it's not proportional to Vg minus V threshold to the square root, which is kind of odd. But even odder yet is the fact that VD sat is now proportional to the square root of the channel length, which is really quite remarkable and quite unexpected. Okay, so now there is one more part of our discussion to wrap things up, and that is an alternative formulation. So far, everything we've been doing for the last half hour or so relied on equation 2213b, and we'll reproduce that in just a little bit on the next page. But this equation works very well for low transverse electric fields, where we have a linear relationship, or for large electric fields, which are much greater than this critical value. The critical value, again, is about 10 to the 4th volts per centimeter. When E is equal to E critical, it breaks down completely, or pretty much. And that's why we developed this thing called a piecemeal. Piecemeal is consisting of 2 parts, and the claim is that it is somewhat more accurate. I probably should have put claimed in quotation marks, because it's not clear what criteria one would claim to be more accurate and what more accurate means, because observation here is really quite difficult. So it's what we're observing, and it's trying to deconvolve all of the different factors which produces the observation. So anyway, that's the claim. So this is equation 2213b, and you can see that for small e's, it's just linear. This term drops out. For big e's, the 1 drops out, and we get mu 0 times E critical. The piecemeal model says the curve is fine until we get to E critical. And at E critical, the velocity, which is the ordinate here, is clamped to V sat, cannot go above V sat. So instead of smoothly going to a V sat, it's kerblunk. It immediately goes to V sat. Where V sat here is about 1/2 the value. In fact, it's not about 1/2, it is precisely 1/2 the V sat of the smooth curve. And we can see that very easily a little bit later. Anyway, so again, we write an equation for IDS. So this is the drain current, output current, and it's equal to the width of the device multiplied by the inversion charge density multiplied by the velocity. Quick unit check. Generally, we start with J, the current density, is equal to NEV. We can also just as easily use the current directly, because the units of W are centimeters, units of Q inversion are centimeters, or coulombs per square centimeter, velocity centimeters per second. So here we have centimeter squared on the bottom, centimeter on top, centimeter on top takes care of the centimeter squared. So this has a second on the bottom, coulombs on top, coulombs per second, coulombs per second. So this is a correct expression for the output current, and we're going to write this in a very special fashion. We're going to write it at or close to the drain, and the condition is that the structure is in velocity saturation and in pinch-off at the drain, but only at the drain. So for VDS, we substitute VDSAT because we're at the drain and it is pinched off at the drain. And for velocity, we substitute VSAT, and VSAT is equal to, well, we have a critical value of electric field. So it's VSAT is equal to mu zero multiplied by mu zero multiplied by E critical divided by 1 plus 1 or 2. So instead of VSAT, we put in E critical mu zero divided by 2. That would not be the case in the piecemeal situation, not in the smooth curve situation, excuse me. In the smooth curve situation, the velocity continues to increase, and we would have twice that amount. So this is the new part right here, is that little 2. And so here we have the current at the drain when the drain is pinched off. Okay. Now we continue. We can also write the current using our previous formulation, using equation 2213b, and this is what we found before. This is the current using the smooth curved approximation, where we have this new term in the denominator. Now, what we're going to claim is both equation 226 and equation 227 describe the same thing, namely the output current. This is at the drain, and this is anywhere along the channel in which we have a condition of VDSAT. So what we're going to do now, since the current is constant, current doesn't depend where you are. Current doesn't change from the source to the drain. Charge doesn't pile up. So we're simply going to equate equation 2226 and equation 2227, and let's see what happens when we do that. And that's what we do in 2228. We're just equating 2227, which is here, and 2226, which is here. This is 2226. This is 2227. They represent, or they describe the same thing, namely the output current. Yikes, there's a lot of bad stuff here. But a lot of stuff cancels out, and you can see it canceling out relatively easily. The Cox cancels out, and the mu's cancel out, and the w's cancel out, and well, we still have a lot left over. So when the dust settles, and this is just basically high school algebra, but you can write it down. It's not that complex. In fact, you can see it relatively easily without all these icky constants here. We just have this term, which on the left side, which is here. That's basically all of this with the E critical on top, and the 2 remains. And on the right side, again, we don't have any of this stuff here. We do have the L, doesn't cancel out. We do have this complete term, and then we have just VG minus V threshold VDSAT minus VDSAT squared over 2. So this is 229, follows immediately from 228, and then we now again define a constant just to make our life a little bit easier here and here. So we substitute this thing called A in there, one on the left side over here, and one on the right side over here. And now we multiply everything out. And by multiplying everything out, I'm basically saying multiplying everything out on the left side. So we have 4 terms, 1, 2, 3, 4, and those are represented here. First term, for example, 1 would be multiplied by A, E critical divided by 2, that's here. And the others follow just as easily, and the right side is the same. And now we can cancel, which is really nice. We can cancel this term, and we can partially cancel this term, and we're left with 1, 2, 3 terms. As these guys go away, and these guys partially go away. These stay the same. So we put the constant term, this guy stays on the left, and everything else, this guy goes to the right. So we take out a VD sat here. And finally, we have 1 over VD sat. Bring this guy over to the right side. And equation 2232 is almost there. The only thing left to do is to say what happens to VD sat when L becomes very small, specifically when E critical times L becomes very small. So when L goes to 0, this term becomes very large. It completely dominates, and VD sat goes to E critical multiplied by L. So remember before, way back when, someplace, oh my goodness, I should have, well, got to be here someplace. This guy here, for very short L E critical, we found it was like the square root. Here, it is linear. So I don't know if that's good or bad. It's just different. So it's probably somewheres in the middle. So instead of being the square root of the channel length, it goes like the channel length to the first power. And the 3 theories of saturation or velocity are contained in the table 22.1. This is the simple theory. This is the smooth curve theory. And this is the piecemeal theory. For long channels, they give exactly the same values. And then we get, for moderate channels, say micron, this stone's long actually. You can see there's a decrease in the VD sat. This is linear, so you expect it to be smaller, and it indeed is. For 0.1 microns, which is still not all that small. Again, of course, this is all the same. Doesn't depend on it. So this is all going to be the same. Here we get a VD sat of 0.09 volts, extremely small. And for 0.01 microns, that's about as small as you can get. And we're basically a VD sat equals to 0. So that's pretty darn dramatic, from 1.54 volts to essentially 0. In all cases, we just use VG minus V threshold of 2 volts, where 2 volts of a threshold and N is 1.3, which is a little bit high, but not too much. And we take the critical as 10 to the 4th. And this paragraph basically describes what we've done in this table. This is a figure which sort of summarizes everything. Electric field at the drain gets extremely large. Basically, it tends to infinity, but of course never gets there. But it gets pretty darn large. Somewheres along the line there is pinch off, and this region would be approximately the region of velocity saturation. Velocity is certainly saturated at the drain for VDS above pinch off, but and it's certainly saturated at pinch off, and it's probably saturated even before we get to pinch off. So basically, this is a summary of everything that we've said. So we finished up now velocity saturation, and we can be very proud of ourselves. So let's end with the marvelous finale to Beethoven's Violin Concerto, played by Hilary Hahn, and we'll see you next time for session 42.